Alright, this is section 2.5. It's all about vectors. Okay, so we're going to kind of discuss what a vector is and then apply this stuff to a word problem. So all this is going to be, a vector is just a fancy word for giving you a direction, or essentially a force, which way is it going, and then how fast, or a velocity. So magnitude and direction. Okay, so what we're going to do is kind of look at it algebraically, and that's really the only one I'm honestly going to really talk to you about. But basically, equivalent, if I say an equivalent vector, all that means is that they have both the same magnitude and same direction. And how a vector is shown is they'll have an arrow going in one direction. All that means is that my vector is going this direction. And the length of the vector refers to kind of its size. What's its magnitude? How far is it traveling? So to be equivalent, they need to be the same length and go the exact same direction. Essentially, they're like parallel lines, but they are exactly the same length as well. So I'm going to kind of talk about this. Head to tail method, that's the easiest visual that I think is happening. Now what I want to show you down here is this is my vector v. Here's its length and the direction. Vector u, here's its length and that direction. All this means is that vector v is stronger, it's longer, it'll go farther, but it's in a different direction as u. W is this one right down here, and then t is this vector right here. Now to be deemed a vector, you say the letter with the little arrow on top. That's just called vector v. That's how we denote it. So if we're actually going to add to, so vector v plus vector u, you just start with the first one and you just draw it out. So vector v looks approximately like that. Okay? Now I didn't copy it. I'm just kind of eyeballing it up there. That's about the general direction. Okay? And then I'm going to add. So a head to tail method literally means here's my head, here's where I end. Where do I start now? The u is going to go basically straight to the right, but not quite as far. Okay? And that's the idea. Here's your starting point. There's your ending point. This is the vector v plus vector u. This side right here that we end up with from beginning point to end point becomes your vector v plus vector u. And this is just how we went about to get there. Okay? Number 2, if I have vector w minus vector v. Okay, so you need to just pick a starting point. I know vector w is going to go down, so I'm actually going to start it down here. So maybe that's where I start. Vector w goes that way, about that far, and then that's where it stops. And then I'm going to subtract vector v. Now we don't really have the idea of what subtraction means, but all that means is vector w plus a negative v. We know that subtraction is just addition with the negative, or add the opposite type of idea. So what is the opposite of v? Well, if v travels that direction normally, what's the opposite? It's going to go literally as it sounds, the opposite direction. Instead of going up, or essentially northeast, or whatever way you want to think about it, I'm going to go down the same distance that it would normally go up. Alright? And then what you end up doing then is now connecting the beginning to the end. And this is going to be your vector w minus your vector v. Okay? And that becomes your r vector, or your ending spot, or however you want to say it. Alright? And then number 3, we're actually going to add 3 of them together. So you just do as it says. So vector v, I'm going to pick a spot. There's vector v. Okay? Then I go here. What's vector w? Vector w kind of goes back down a little ways. A pretty good distance as well. Stop. And then vector t. What does vector t do? Kind of goes a little bit farther down in that direction. That's probably a little too far. Maybe it should be more like that. Okay? But you just go one, then the other, and then the other. And then wherever we end up, that's where we will connect. And then from beginning to end is your little addition problem. So vector v plus w plus t. Okay? And that's your ending vector. And that's kind of how that all works. And that can be denoted in a lot of different ones, which is with a different vector. Maybe your result vector, r vector, a lot of times will be denoted instead of actually writing out the method like that. Okay? There is another way to do this. It's called the parallelogram method. I'm just going to show you with one of them what it is. I like doing the adding and figuring out where we started and where we ended up. The parallelogram method just means that if you have v and u, you actually do both of them from the same spot So this would be your u vector. Here's your v vector. Okay, and they want you to make a parallelogram. So imagine that you would actually put u here and put v there, and then the diagonal ends up being where you end up. Well, to be honest with you, that's more work than putting the other ones on there, because you're actually making 4 lines instead of 2. So to me, this isn't as easy, but it is another way that the book might show you if you kind of page through the book. Okay, let's actually get into the meat and potatoes of this lesson here. So if I have a boat crossing a river, okay, it runs due east. So here's my not so wonderful artistic skills. Here's my river. I'm going to make it be about 4 wavy lines. So imagine that being the fancy river. The boat is going to cross due south. Okay, so I have a boat. I'm not going to draw a boat. My boat's going to be a circle. It's a dot in the water. Okay, and I know that this thing's traveling due south at what? How fast? 11. I better write this in a different letter. 11 feet per second is how fast it's traveling. Okay. At the same time, if the current of the river is 2.5 feet per second, okay. Oh, the river runs due east. I forgot to tell you that. What that just means that the river's flowing this direction. I should have probably said that first. Okay, due east is straight to the right. So I know that the river current is going to push you towards the east, even though you're traveling a little bit south. You're going to float east with the water. I know if a lot of you ever tube in the water, just lay in the water, you're going to go with the current. So even if you're traveling in a boat, you actually do move with the current unless you turn. And that is traveling 2.5 feet per second. And it says find the true course of the boat. Okay, true course. What do we want with the true course? True course is all about how it's stated in the problem. Okay, so basically what we want to do is true course means what angle are we actually traveling, because I'm supposed to be going due south. This river's pushing me, so this is where I'm ending up. So what we want to do is actually find this angle in there. Okay, so how about that? How am I going to figure that part out? Well, from this angle inside, I know I basically do not have a hypotenuse. So you always want to find that right angle. That'll always show up. I don't have it, so I now have the opposite and the adjacent. So if I have the opposite and adjacent, I know I need tangent. Okay? And tangent theta is going to equal what? Tangent theta is 2.5 over 11. Okay? And if I want 2.5 over 11, tangent inverse of that's going to give me my angle. Okay? Theta equals, and if you do that, it's going to be 12.8 degrees. Now, to actually give me the true course, what direction is the boat actually moving? So what you want to do is kind of think about this as kind of a crosshair starting point, and I'm traveling starting south, traveling towards the east, 12.8 degrees. That's supposed to be a decimal point in there. So my true course would actually be south 12.8 degrees east for a bearing. Okay? To actually figure out how fast the boat ended up going, you could just find this side. Now that's not necessarily written in here, but if I did want the speed, you could just simply do Pythagorean theorem. So if I did 2.5 squared plus 11 squared equals c squared, and you add these two together and then take the square root, c is going to be 11.3 feet per second. So actually with the current going straight sideways, you do gain like 0.3 of a mile per foot per second. So almost 1 foot per second gain, even though the currents, it will help you travel. Okay, so that'd be if I actually want my ground speed or true speed would be actually be 11.3 feet per second in that same time period. Okay, but if I just ask for the true course, you just want the angle, and there'll be a few more examples of this now. Okay, if I ask you about navigation, I kind of did the bearing before because I haven't talked about this, but you also have what we call a heading. Now just to mess with you a little bit more, a heading is simply just, if I talk about this, 120 degrees from due north in the clockwise direction. So if I ever say anything about a heading, that's just an angle, and it's always from due north because it's based off of a compass. So like a lot of navigation and all that stuff, that's what it's kind of for. So if you have a compass, you can go and work that way for your direction. But just in this purple one, 120 degrees due north clockwise direction, this is what kills us because it's different than what we are used to. That's 90. Here's 30 more. I would be going actually, what, southeast direction on a bearing, actually on a navigation, a heading of 120 degrees. Okay? And then if I say I'm traveling 14 miles per hour, that would be how fast I'm going in that direction. So just another example of this, if I say a plane has an airspeed of 140 degrees, all right, and a heading of 130 degrees. So if you have a heading problem, okay, this is due north, and I always start from due north, go clockwise. So there's 90, and there's going to be about 40 more beyond that. And I know that I am traveling how fast? 140 miles per hour. Okay? And that's where I'm going to end up. So I know that this whole thing is 130 degree heading. And now, I might need to erase that actually. I'm going to include the wind speed. Now, if you guys are in an airplane, a lot of you have flown before, it's amazing that sometimes you get to the destination faster and sometimes it's slower, all hinging upon the wind speed. Okay? So now in this case, the wind is going to be constant at 14 miles per hour in the direction of north 40 degrees east. So what I want to do is go back to the vector idea. The reason I like the whole adding them together is now I'm going to put like my airplane, and then I'm going to do the wind speed right after it. I'm going to add it on. Okay, so what I mean by that is here's my airplane speed, and then I'm going to reboot my crosshairs, and I'm going to redraw in what my wind's doing. So my wind is north 40 degrees east. So what we need to do is from this top, north 40 degrees east is my wind direction, and that's 14 miles per hour. Okay, so I know that this is 40 degrees in here. And what we want to do then, it says ask for the ground speed and the true course. So ground speed is literally your hypotenuse. It's from where we started to where we ended. Can you find that number? Now in all of these problems, there will be a right angle. We got to figure out how to get it. Okay? So my original problem had a heading of 130. This guy is 90 and that much more. Okay, I'm not exactly sure what that part is, but I know it's 130 from the top all the way down. Now this red line is not necessarily going to be straight east. I can't assume that. The one thing I can assume though is from north to due south is 180. Okay, so if I know that's 180, this is where it gets kind of tricky. I know this angle in here has to be 50 degrees. Because 130, my original heading, plus the 50 has to get me straight up and down. Now, why am I telling you all this? Because I need to convince you that this is a right angle. Now, why is that going to be a right angle? Because I have 40 degrees in there, and this spot here needs to be 50 degrees. Now, why do I know this? Because if you think back to alternate interior angles from geometry, okay, this is going to be a line straight up and down, and this guy will be a line that is going to be parallel. Your crosshairs become your best friend. This is parallel to the bottom. So if this angle in here is 50 and our hypotenuse is your transversal, this has to be 50 degrees. Alright? Now that's a big long spiel to tell you that this is a right angle, but I promise you in every single problem there will be a right angle. Now why is this helpful? Because now to find my ground speed, I need to find x, which is that hypotenuse distance. And since you have a right angle, you just can use Pythagorean theorem. 14 squared plus 140 squared is your x squared. And then you end up getting that x equals 140.7 miles per hour if you solve it correctly. Now that is going to be my ground speed. That means actually instead of flying 140 miles an hour like the speedometer shows on that plane, you are traveling 140.7 miles an hour, because this wind is, even though it's pushing you left, it is actually helping you travel faster. Okay? And that's why you can get to a place faster on a plane, because if you have a 30-mile-an-hour jet stream wind helping you go, you're going to get to a place a lot faster. Now the last thing, the hardest one for everybody to do, and I know we're going to practice these, is finding that true course. Now this has to be written in the same denomination as the actual plane was given. So the plane was given in a heading, so we need to give it in a heading. Now what gets hard is this. You need to find the angle that has changed. Okay? It was 130 degrees from due north all the way to that original side that the plane was going. Right? What we need to do now is find the angle inside of the where you ended to where you were going. And I need to subtract that from 130, because I'm not going as far north and, or actually as south and east as I was. I'm going to go kind of more east and less south. So I'm going to kind of figure out it's not 130 degrees. It's going to be closer to like 90 degrees or just a little over 90 degrees. And maybe it's more than that depending upon how my picture looks. Okay? So what I need to do is this. I need to find that green theta. Now to do that, I still have a right angle down here. So I have the opposite side and the adjacent side. By knowing that, I can take tangent theta equals opposite over adjacent. And I can find that theta by taking the tangent inverse of that fraction. And that's going to be equal to 5.7 degrees. Now, why is that helpful? That tells me that I do not need to go 5.7 degrees as far as that original setup. So to find my actual true course in this particular problem, the wind is going to push me, instead of going 130 degree heading, it's going to push me 5.7 degrees less than that. So you end up getting 124.3 degree heading from the very beginning to where you actually end up. Okay, this would be 124 degrees, 0.3 degrees. Now some of you probably are like, whoa, that's crazy, but those are the type of problems that we need to work on. So 2 more problems to go. I'm going to do this one relatively quickly. Human cannonball shot from a cannon with an initial velocity of 50 miles an hour at an angle of 60 degrees from the horizontal. What you need to make the connection of is this. Okay, horizontal is like the ground. Okay, and I am shooting something 60 degrees from the horizontal. That just means that's a 60 degree angle. Okay, and I know that it's traveling, that should be a straight line, but you guys can work with me on that, 50 miles per hour. Alright, and all it says is find the horizontal and vertical vectors of that velocity. So I know that this thing's traveling that way 50 miles an hour. It actually wants you to find, okay, how far or how fast is it actually moving straight east, and how fast is it actually moving straight north, or vector, horizontal vector, and your vertical vector. So I'm just labeling them X and Y, and you have a right angle, 60 degrees, and you have the hypotenuse, so you just do one at a time. So to find your horizontal vector, alright, that's the X, or the adjacent over the hypotenuse. So I'm just going to go quickly, cosine of 60 degrees equals X over 50. So my horizontal one is going to end up being 25 miles an hour if you multiply 50 to both sides. To find the vertical one, I have an angle, I want the opposite, I have the hypotenuse, so that's going to be sine of 60. And you multiply 50 to both sides again, and you end up getting that Y equals 43.3 miles per hour. So if I ever ask you for the horizontal and vertical vectors, that's all it means is you want to find the one that's straight on the bottom and the one that's straight up, and most of the time you're going to be able to use sine and cosine for that. Here's the one that gets tricky. We're going to do this one, a bunch of like these in class again, but here's where it kind of ties everything together. Not only does it give you a speed, it gives you a time. Okay? So all that does is that really messes up what your side lengths are going to be if they give you a physical time, because it's one thing to travel 22 miles an hour, but if you travel 22 miles an hour for 1.5 hours, how fast do you actually go? You actually go 33 miles. So what you're going to need to do is figure out, is it just a speed problem, or is it actually asking a distance problem? And that's how you go about finding your distance. So let's actually put this on the thing. If a person bikes that fast in a direction of north, 37.5 degrees east, okay. I'm going to start here. And I probably shouldn't even do solid lines either. I'm going to do some dashed lines to try and make this less confusing, even though this gets messy. I'm going to say north, 37 degrees east. That's that. So this is 37.5. Okay. How far did I say I was traveling? Okay, 22 miles an hour for an hour and a half. So I actually traveled 33 miles. That is this distance, 33 miles. Okay. And then I'm going to reboot. It says then we change directions to south 52.5 degrees east. So if you ever change directions, here's where I would reboot my crosshairs. Okay, and now I'm going to actually start south 52.5 degrees east. Now how far is this person going? 18.5 miles an hour for 2 hours. That ends up being what, 37 miles? That's a long time on a bike. Traveling, what, 70 miles? That's a long ways. Okay, so 37 miles. That means this thing is actually going to be a little bit longer than the first one. So I'm just going to kind of draw it that way. This one's 37 miles long. And this angle inside, now this was 37.5. This guy in here is now 52.5. Alright, and I want to find what? At the end of this time, how far is she from her starting point, and what is the bearing? Okay, we need to find a distance and a bearing. Now the distance, straightforward, because I told you in every one of these problems there's a right angle. Now what is that right angle? You should hopefully kind of recognize this in here will be a right angle. Why? You have your beginning line and your beginning line that are parallel. This is your transversal, so this 37.5 degrees that we initially started here will also be 37.5 degrees in there, and 37.5 and 52.5 will add up to your 90 degree angle. So once you find your 90 degree angle, this becomes relatively nice because one side's 33, the other side's 37. Your actual distance, how far is she, is just your hypotenuse. So we can do the Pythagorean theorem, and we'll say c squared is our actual distance. And if you add all these together and take the square root, c is 49.6 miles. Okay, so the actual distance is 49.6 miles. And now what they also want you to do is the bearing. Now what is bearing again? If I ask for bearing, that's the whole north, south, east, west thing. Alright, so what we need to do is from start to end, what is the bearing? So am I actually traveling north from the start to the finish, or am I traveling south? At this point, the way my picture looks, I feel like it's from the north. And if I feel like it's from the north, I need to start due north, kind of like I was, and I have to get all the way down to that pink line that is my actual distance that I traveled. So I already know that the top part is 37.5. I need to figure out this angle inside my triangle so I can add that on to 37.5 to get the actual degree measure from north towards the east. So to do that, the two sides I have are the opposite and the adjacent. So once again, we're going to use tangent. It's kind of a norm in this problem, but tangent theta will be the opposite's 37, adjacent's 33. Take the tangent inverse of both sides. Okay, and you end up getting an angle of 48.3. Now that is not your bearing, because 48.3 is just part of it. So we actually have 37.5 and the 48.3. Your bearing is north. 37.5 plus 48.3 ends up actually being, what, 85.8 degrees in the east direction. So that would be your bearing. Whew. Some of these problems get long. I apologize for how long this is, but I know it's nice for some of you to go back and kind of talk about this, see it, if you need it. Now, once again, if you are completely lost, that's okay. We're going to work on a bunch of these in class, and I hope that some of this is starting to sink into you. So just remember that you will always get that right angle, and we will continue to work on these as we progress through the day tomorrow and in the next week. So I hope you have a wonderful day.